Hi, everyone. Let's try that again. Hi, everyone. Awesome. I like to come stand over here because these people thought they wouldn't participate because they sat in the corner, but they're not going to get away with that. Welcome to this talk on using Vault. How many people here have heard of HashiCorp before? Okay, how many people heard of HashiCorp before Paul Stack's talk this morning? Okay, cool, cool. See, you influenced a few people, Paul. So I'm here today to talk to you about Vault. Vault is a tool for managing secrets in an organization. How many people here work for a company? Nonprofit, regular company? Okay. This is an interactive thing. I don't know if you figured that out yet. How many people here would say they work for a startup? Okay. How many people here would say they work for like a mid-sized company, like less than 500 people, let's say? How many people would say they work for an enterprise, more than 1,000, 1,500, 2,000 people? Okay, so I want to take you through a journey, and I have no slides, so you have to pay attention. This is an interactive exercise, and I'm going to take you on a journey right now. How many people here consider themselves a developer? Okay, how many people are more on like the operations or sysadmin side? Okay, this is for both of you. How do you get a database credential? Just think about that. Don't tell me. Just think about it for like 5 more seconds. If you're a startup, the way you acquire a database credential, let's use something like Postgres as a concrete example. You Google, how do I create a Postgres user? You copy and paste some stuff from Stack Overflow. Then you SSH into the production machine, and you create your user, and you copy and paste it into a text file somewhere. If you're a medium-sized company, you probably have something like maybe like Chef or Puppet or Ansible or Salt, some type of automation. Maybe you have like a little portal where you can go in, but you ultimately take that credential and you put it in a text file somewhere. And if you work for one of these bigger enterprise companies, you file this thing called a Jira ticket, and you wait 6 to 8 weeks to get your database password back from the DBA team, and they email it back to you in plain text, and then you put it in a text file. And these are all problematic. And there's a number of problems with it. The first is that once that credential is created, it tends to live forever. Even if you rotate the credential, do you actually go into the database and delete it? The second is that there are a number of humans who know that credential. They have seen it through emails or ticketing systems or putting it in the config file. And if you're checking that config file into source control, then anyone who sees that config file has access to see those secrets. That's a challenge because whenever we're looking at anomaly detection software, or we indicate there's a breach or something, we don't actually know where or who or what caused that leak. If we're running multiple instances of our application, let's say we have like a typical 3-tier web app, or we have multiple front-end servers that are all communicating to the back-end database, we don't know which one of them actually leaked a credential because they're all using the same one. The third problem is in that situation where we've identified a breach, let's say we're in a situation where we've identified that our secrets are being leaked and we want to stop it. We can't adequately predict what will happen when we do that. We don't know, we have limited visibility, limited centralized access into whenever we change one of these secrets or delete it or revoke it, what's going to happen? Is it going to take down all of production? Are there other people in the organization relying on that secret? People in marketing, people in analytics and accounting and business operations who are using that same credential that if you revoke it, you're going to break some nightly batch job or cause someone else pain in the workplace? And the fourth problem, and probably the most important problem, is how do you actually revoke them? So if you're in a situation where you have detected that there's an intruder on your network or there's a breach in your database and you need to stop the hemorrhaging, you need to mitigate as much as possible, how do you delete those users? And how do you do it quickly without affecting everything else? And we call this like the break glass procedure. It comes from in the US and other countries, you have to like break the glass to pull the fire alarm or to get to the fire extinguisher because it's in case of emergency. And we hope as an organization that we never have to get there. We never have to pull that fire alarm or put out the fire. But it's also important that we have fire drills and we test the fire extinguishers because when something does go wrong, it's important that they work 100% of the time and with 100% reliability. So those are the 4 main problems that I'm going to talk about. limited visibility, poor insights, lack of a break glass procedure, and more than one person knowing the credential. We call this like lack of some big word that starts with a P that's not relevant right now. So that's my intro. So I want you to keep thinking about this, right? How do you get a database credential? This is the whole mantra of the theme here. And now I'm going to talk about Vault. So we're going to switch gears a little bit, and I'm going to show you some pictures. Who's excited? Put this in here. All right, I'm pretty loud, so I assume y'all can still hear me. So this is Vault's architecture. Vault's architecture is designed. This is Vault's architecture. Vault's architecture is designed such that any and all requests happen through the HTTP API. So Vault at the top there has an HTTP API. There is no way to interact with Vault that does not go through the API. So there's no RPC calls, no fancy whatever. It's just an HTTP API. And that should be exciting, and that should maybe set off some bells and whistles, because if it has an API, it can be automated. There doesn't exist a programming language on the planet today that doesn't have a way to make an API call or make some TCP connection to some remote server. So that means you can communicate with Vault via any programming language or configuration management language like Chef or Puppet or Ansible or Salt. They can all communicate with this because it's just a JSON API. Once a request hits the API, it goes into the barrier. The barrier is this cryptographic seal around the Vault. Any and all requests have to flow through that barrier, and that barrier is locked by a key. And this is going to become important when I show you the unsealing process. That barrier doesn't allow requests to flow through it if the vault is not unsealed. So if you think about a bank vault, you walk into the bank, you get your money. Typically, that's a big metal door made of titanium and plated glass in the middle that 2 or more keys have to come together to unlock that. The bank manager and maybe a regional manager or another employee both have to put their key in and turn them at the same time to unlock the big vault door, and then you can open it and get to the money. This vault behaves the same way. We'll talk about that more in a second. In Vault, we have the core. The core is broken up into 4 pieces: the token store, the rollback manager, the policy store, and the expiration manager. We'll get into those more in detail on how they actually apply to the system, but tokens store tokens. The rollback manager and the expiration manager are responsible for rolling back in the face of failure and expiring credentials. And then the policy store is just a database of where the policies are stored. Off to the right here, you can see audit backends. Every request and response in Vault is audited. So every request you make and the response that Vault gives you back is audited and logged. And there's a number of different places that you can do that. And then every request in Vault is path-based. So /foo actually routes to a particular backend, and /bar routes to a different backend. So you can see there in the middle that path routing. What Vault does is it strips off the beginning of that, routes that to a particular backend, and the backend handles the response. Some backends will write directly to this storage, the durable storage on the bottom. Some backends might communicate with third-party APIs like AWS or Postgres or Microsoft SQL, and some of them might go out to something like GitHub or an LDAP server to authenticate you. So you can think of these, like the system backend and the secret backend and the credential backend, as remote API calls or plugins. And they perform some operation and they return data back to Vault's core. Vault's core then returns that data as part of the response to the request. And that down at the bottom there, outside of the barrier, we have the storage backend, which is just the durable storage. That's where Vault is going to write the persisted data. That data is encrypted in transit and at rest, meaning it's never going to be left in a state where it's unencrypted. There's a number of storage backends you can write to in memory, in which case Vault runs entirely in memory. You can write to the file system, but you can also write to a database or a distributed key value store like etcd or Consul. So let's talk a little bit more about this barrier thing. Vault uses this thing called Shamir secret sharing algorithm. And what Shamir secret sharing algorithm does is it allows us to take a string, effectively, and we can split that string into a number of shards. So imagine I took a literal string and I cut it into 5 pieces, and I gave 5 people in this room a piece of that string. Magically, through mathematics and Shamir's secret sharing algorithm, we would be able to reconstruct that original string by a subset of those people giving me their string back. So in real world material science, it's not possible, but when you start talking about elliptical curves in a 4D space, it is possible. So what we do is we take a string, a series of bits, and we break it apart into a number of configurable shares. And that's a key, and we give that to trusted people in the organization. A subset of those people, which is also configurable, must then supply their key to Vault in order to unseal it. This is important because this also closely relates to the barrier. The barrier is encrypted with that encryption key. So the barrier isn't just like an if Vault equals sealed or unsealed. It's actually Vault can't serve requests unless it has that encryption key. So when you first start up a Vault server, you're going to initialize it. That initialization is going to generate this master key and break it apart into a number of key shares, and you distribute those to people. From that point forward, Vault never stores the master key. It only existed in memory, and it does a GC purge when it's done. The result is that that master key encrypts the encryption key. The encryption key is the thing that actually does the encryption of the durable data on disk. It does the in-transit encryption if you're not using TLS. But that master key never exists beyond its initial creation. So the only way to decrypt the encryption key is to have all of these key shares or a subset of these key shares come together to regenerate the master key, which will decrypt the encryption key. So this is very similar to how in a bank, 2 or 3 or 4 people have to come together and physically put their key into the bank vault in order to unseal the vault. This is the same, except it's using algorithms and cryptography instead of a physical key. And a subset of people can come together to unseal the vault. The reason we do this is because one of Vault's design goals is to prevent one person from having complete access in the system, because that's a single point of failure. It's a security vulnerability. If we imagine a situation where Alice is the only security researcher at a company and Alice is the Vault administrator, when Alice leaves the company, nobody's maintaining the vault. If Alice decides to go rogue and harm the data or sell data to another company, there's no one to stop it. There's no checks and balances. So Vault is designed in a way that no one person has complete control of the system. It requires a quorum of people to perform sensitive operations like unsealing of the vault. So that's Vault's architecture. So let's actually use this thing, because this thing said live demo, so I suppose I actually have to do a live demo. All right, so Vault is an HTTP API server as well as a command line interface. They run in the same binary. So it's like a 6 megabyte binary, single static binary, no dependencies. You download it, put it in your path, and you're good to go. And then you get a Vault. So this is the Vault CLI. You'll notice that there's a number of commands here. There's a Vault server command that'll start up a Vault server. I can give it some config flags. I'm not going to show you that here because I already have one running. But there's also like a Vault status command, a Vault write command. So the Vault agent can run locally on the CLI, but it can also run as a server. It's the same binary, no special mode, nothing like that. So I have a Vault server that I've configured out on the cloud, if you will, and it's already unsealed and ready to go. I didn't want to walk you through me copying and pasting strings into a terminal. That's not exciting. But you can see the Vault server is ready to go. I'm not running in high availability mode. Vault does support high availability mode. You can run 3 or 5 instances and they can fail over if you're in a situation where you desire high availability. But for this demo, I'm just doing a single instance. It's running the latest version of Vault, which is Vault 0.6.2, and it has a cluster ID, which is not something that's a secret. This Vault is running, and just like a web application, I can see a little bit of data, right? I can Vault status without being authenticated, just like I can hit the home page of a website without being authenticated. But if I want to perform any interaction, I want to edit my profile or search for users or something like that, I have to log in. So just like you provide a username and a password to log into a web app, you provide some type of authentication to Vault. And Vault supports a number of different authentications. You can log in via GitHub, kind of like OAuth. You can log in via LDAP or Active Directory. You can log in using a username and password that's built into Vault's internal database, or you can log in directly using a token. And that's the equivalent of like going into your browser and manually setting a cookie. But for now, I'm just going to authenticate as the root user. And I cheated in advance and created a root user named root so that I could remember it. So I'm now authenticated as the root user. In Vault, the root user is kind of like sudo or like su. It's like the super user. I can do anything in the system. This is a live demo. You should not do this in real life. In fact, you should not have root users in real life after you configure Vault. But for the purposes of this demo, it works out really well because I don't have to jump back and forth between a bunch of different policies to show you really cool stuff. There are two kinds of secrets in Vault: static secrets and dynamic secrets. Static secrets behave a lot like encrypted Redis or encrypted memcached. What I'm about to do is I'm about to interact with Vault, and you're not going to be impressed because it's not going to feel secure. It's not going to feel great. So let me show you that. So I'm going to write something to Vault, which is I want to store something in Vault. I'm going to put it in secret/foo, which is secret is a path that's going to get routed to a backend. The rest of that payload gets sent to the backend, and the backend does some processing with it. And I'm just going to say value equals, I don't know, banana. So I've written this data to Vault. This local Vault CLI made an API call to my remote Vault server that's running on the cloud with this data over TLS. Excuse me. That data is now stored in that Vault server, and I can retrieve that data by reading from the same path. And you'll notice back I get the value is banana, and there's this refresh interval, which is 768 hours. That didn't feel very secure. Like, how many people feel more secure now? Yeah. I'm insecure all the time, so it's fine. And this is something I always like to discuss because Vault has been audited multiple times by very reputable organizations. And it is secure. It's one of the most secure tools in the security space right now. I can't name customers, but I can say that if you've engaged in a financial transaction in the past 24 hours, you have indirectly interacted with Vault. It is highly probable. So it's used by massive Fortune 500, Fortune 100 companies. They trust it. So why doesn't it feel secure? Well, as humans, we've been conditioned that security has to be hard. How many people here have worked with PGP before? How many people remember the commands they need to do to verify a PGP key? No, you just Google it every time because it's so complex. And oftentimes it's unnecessarily complex. And with Vault, we use state-of-the-art algorithms and encryption, but we've done our best to wrap that in a user experience that feels right. The downside is because it feels right, it doesn't feel secure, but I promise you that it is. Security doesn't have to be hard. Oftentimes, we mistake security for obfuscation, which is we need this painful process in order to get a secret value. But that's not actually more secure than using something like modern AES encryption. I can update these values, so even after the value exists, I can update the value to be Apple, and these are actually key value pairs. So value isn't anything special. I can say A equals B and C equals D in here, and all three of those things will get written. So when I read that value back out, you can see A equals B, C equals D, value equals Apple. So you can write any arbitrary string equals string data into this particular backend, and it's stored, it's persisted. So even if we stop the Vault server, this is persisted on disk, it's encrypted. When we restart the Vault server or bring it back online, we'll have to unseal it, and then we'll be able to retrieve these values. We can also list secrets. So we can list all of these secrets. So that gives us all of the keys under that particular secret. There's just one in this case. And we can also delete them. So we can delete secret/foo. And that secret's gone, and now if we were to list again, there's no secrets there. So it's a very basic CRUD, create, read, update, delete system for interacting with secrets, and it's static. So it behaves a lot like encrypted Redis or encrypted memcached. What you put in is what you get out. We can attach policies to all of these paths. So I can give a particular user the ability to read but not create, so read-only user. I can give update only or create only, which gives you like atomic users. I could create delete only for maybe like an external process that should just be doing maintenance on this. The static secret backend is really good for things that don't change over time or are unlikely to change in a short interval. Things like Wi-Fi passwords for the corporate network, if you don't use something like radius authentication, or maybe like the door code to get into the bathroom at the office, right? That's where the static secret backend comes in. The dynamic secret backend is where Vault's power really shines. Sometimes you'll hear people call Vault a secret acquisition engine. What this means is Vault actually goes out and generates credentials on your behalf or on an application or machine's behalf and returns them as part of the response. We'll talk about some of the advantages and the disadvantages there. How many people here run on AWS or something on AWS? Wow, that's a lot less than I expected. It's okay. How many people know what AWS is? Okay. So if you've never worked with AWS before, if you want to communicate with Amazon via the API, you need two pieces of information. You need an access key ID and a secret access key. It's kind of like a username and password, but completely different. In order to get those, you have to log into the UI, you have to click 6 dropdowns and 3 next, next, next buttons, and then you copy and paste some things from a web UI, and you somehow get them to a person, right? How many people have gone through that process before? Yeah. So wouldn't it be better if there was a better way? Well, with Vault, Vault can actually programmatically generate access keys and secret access keys for us on AWS. So let's take a look at that. Remember, everything in Vault is path-based. So we have to tell Vault to mount a particular path with a responsibility. So just like a file system mount where you say, /bar is going to go to this NFS share or, this CFS pool, I'm going to say /AWS is going to go to the AWS backend. And the way I do that is via the mount command. So Vault mount AWS. I've now mounted the AWS backend at the AWS path. So anything I write to or read to from Vault that starts with AWS/ is going to be delegated to this backend. And that backend is actually the thing that has all of the logic and the responsibility for communicating with Amazon. Now I need to tell Vault how to talk to Amazon. It doesn't know which account I want to create users in or what policies I want to do. So I have to give all that information to Vault. And this is where people get a little bit weary. I'm about to give Vault some very privileged credentials. I'm going to give it an access key and a secret access key that are privileged so that it can create users on my behalf. But it's always better to have a machine that's fully audited, every request and response, have these credentials than a human or an operator who can make mistakes, who can leak those or give them to other people, and there's no tracing and there's no flow of information there. So I'm going to go ahead and configure the AWS backend, and the way I do that is by writing to AWS config root, and then I have to give it the 3 things that you always give to AWS, which is your secret key, your access key, and your region. So I'm going to give it my access key, which is conveniently stored in an environment variable, so you all don't get to see it. My secret key, which is also conveniently stored in an environment variable, so you all don't get to secret key. And AWS region equals AWS region. Okay, so that data was written. So I just uploaded that data to Vault. Again, this is a remote HTTPS JSON API request. And now I need to tell Vault how long I want these credentials to be valid for. Right now, if you create an access key and a secret key in Amazon, how long is it valid for? Ever, right? It's valid until you go and delete it. With Vault, we like to treat secrets more like DHCP or DNS leases. Everything has a TTL. And after that lifetime is up, unless you have renewed it or you've said, hey, I'm still using it, then we revoke it. And that reduces the surface area for an attack because it prevents us from these ever bubbling up generation of credentials. If I generate an AWS credential and I set its lifetime to 24 hours, if it doesn't get used within 24 hours, Vault will revoke it. That means you don't have a credential just lying around. So let's go ahead and configure that. So AWS config lease, and I'm going to say that these credentials are valid for, the default is 5 minutes, and the maximum they can be valid for is 15 minutes. So what that says is this credential is valid for 5 minutes. So when I generate it, it's valid for 5 minutes. That's the minimum lease time unless it's revoked early. I can renew it. I can keep telling Vault, hey, I'm using this, hey, I'm using it, hey, I'm using it, up until 15 minutes. And then after 15 minutes, Vault is going to revoke it even if you're still using it. So this allows you to set the maximum lifetime of a credential. This is just a demo, so these are a little bit shorter. In reality, you would have a lease that's a lot closer to maybe 24 hours and a maximum that's closer to something like 7 days or 30 days, depending on the type of credential. These are all configurable, so whatever you want to configure, you can configure based off of your policies. Speaking of policies, when you create a user in Amazon, you have to tell Amazon what permissions to grant that particular user. Do you want them to be able to launch EC2 instances? Do you want them to be able to interact with S3? And you do this via these really fancy JSON files that look something like this. So this is just a very simple policy that gives IAM access to the user that's getting created. What we're going to tell Vault is to attach this policy to the users it creates, because otherwise I have a user that has no policy, no privilege in the system. And the way we do that is we upload this policy to Vault. So we go Vault write, AWS roles. Then we name this role. So I'm going to create a developer role. So I'll create developer, and I'll give it this policy. And Vault supports reading from a file path, just like curl, by passing in the @ sign. So I wrote that data. So now anytime we generate a credential from the role developer, it'll attach that policy, go out to Amazon, generate the access key and the secret access key, return it to us, and we can do whatever we want with it. So let's test that out. We can do that by reading from AWS Creds developer, and hopefully this works. It did. Yes, live demo gods are with me. So you can see here, this is an access key and a secret key, and that took a little bit of time, right? It took like 2 or 3 seconds. That's because my Vault server actually went out to Amazon, initiated a connection with their API, generated a user, attached the policy to the user, and returned that to me. And you'll notice if I run this command again in 2 or 3 seconds, I'll get another access key and secret key. And if we were to log into the Amazon console right now, you would see 2 IAM users that both have this policy attached to them. You'll notice they have a lease duration of 5 minutes, and that's an indication that after 5 minutes, unless we tell Vault we're still using this credential, Vault's going to go ahead and revoke it. So you have 5 minutes to hack my AWS account. Please don't. This is important that every time we read from this, we generate a new credential. I'll do it again just to prove it to you. You'll notice that we're getting different access keys and different secret keys. If for some reason we think we've been leaked, like, oh crap, this is a recorded session, and I need to revoke these credentials, I can do that by running the Vault revoke command, and I can just give it a path. So I'm just going to revoke all of the credentials under the AWS Developer Endpoint. So that's going to revoke all 3 credentials I just created. So if you were trying, I'm sorry. They're gone now. And that's how fast we can respond to a break glass procedure. If we think someone's in our AWS account, the AWS rep calls us up and says, hey, are you actually running 500 C34XLs? And you're like, nope, you just Vault revoke. That'll definitely sever any IAM connection, and then you can repair from there and look forward to your $100,000 bill. Okay, so this is AWS credentials. We can create multiple roles. So let me go ahead and edit this policy here. And I'm going to edit this policy to be EC2 instead of IAM. And I can generate another role named something other than developer. So let me write to AWS roles. What do we want to name this role? Okay, devternity. Did I spell that right? Yeah. Devternity, we'll give it a policy that's that same policy, but I edited it. So we've created this new role, and I can read from AWS Creds devternity, and that's going to generate something that looks the same, right? It's an access key and a secret key, but those have a different policy assigned to them. And because everything in Vault is path-based, I can give Vault users access to AWS Creds devternity, but not AWS Creds developer. So they can generate EC2 instances, but they cannot generate new IAM users, or vice versa. Because everything's path-based, you can use things like regular expressions and short and long matching in order to match on a path or a subpath to grant users access in Vault. Right now I'm the root user though, so I can kind of do anything. So that's one example is AWS. In this case, Vault is going out to some external API, making some API calls and getting data back. Let's look at something like Postgres. So Postgres is a database, just like MySQL, MariaDB, or the whole 9 yards. I'm going to go ahead and mount the PostgreSQL backend. So this is going to be able to communicate with Postgres for us. Again, it'll be at the PostgreSQL path, so anything that starts with PostgreSQL will be relegated to this backend. Now I need to tell Vault how to talk to Postgres. Postgres could be running at localhost. It could be running on an RDS instance. It could be running, in some other cluster somewhere. So I have to give Vault the username, the password, the URL, the port, the database, all of that information, and we do that via a connection URL. So I have this connection URL here. This is the username and the password are randomly generated by another HashiCorp tool called Terraform, and that's the IP address of the Postgres server, and the database name is my app. So I'm not going to type that out. I'm going to go ahead and just write that to PostgreSQL config connection. Connection URL is at connection url.txt. And we get a little warning back that's like, hey, you wrote a thing that included plain text credentials, so make sure you secure this path because otherwise someone could read those values back out. That's okay because Vault is deny by default. So unless you explicitly grant access to AWS or to PostgreSQL config connection, no one will be able to read these back out unless they're the root user. So we've configured Vault to talk to Postgres. It actually validated that connection, so I know I didn't make a typo. It went out to Postgres, made sure it would connect and have the proper permissions in order to interact with the Postgres server. So now I need to give it that default lease. So we'll go ahead and write to PostgreSQL config lease, and we'll do the lease is going to be 2 minutes, and the lease max is going to be 1 hour. So any credential I generate is valid for 2 minutes. I can renew it for up to 1 hour, at which point I have to get a new credential. The last thing I have to do is I have to tell Vault how to create a user, right? Vault doesn't speak Postgres, and it doesn't know what kind of Postgres user we want to create. Do we want the user to have read permission or write permission? Should it be able to drop tables, right? Just like a SQL grant statement, we have to tell Vault, hey, this is the user you need to create, and we do that by naming a role, just like AWS. So we write to PostgreSQL config roles, or sorry, creds, and then, I lied. We write to PostgreSQL roles, and then the name of the role, which in this case we'll call it read-only, and we actually just give Vault the SQL that we want to run. But before I run that, I want to show you that SQL. So that SQL looks like this. I'm going to create a role with a login password that's valid until an expiration, and then I'm granting select on everything. So this is a read-only user. So what's up with those curly brace things there? Well, those curly braces there, the name, password, and expiration, are going to get filled in by Vault. So Vault's going to generate those values and interpolate that template, that SQL, when it runs it. The valid until clause is really important because that means that in addition to Vault going out and revoking the credential, Postgres will also revoke the credential after a period of time. So if someone's able to DDoS the Vault server or take it offline, Postgres will still revoke the credential. So again, Vault write PostgreSQL roles read-only SQL equals add read-only.sql. Okay, so now we uploaded that role. So now Vault knows how to talk to Postgres, what it should create the leases with, and how to actually create the user. So now we can read from PostgreSQL creds read-only. And you can see that one was a little bit faster. That's because coincidentally this Postgres server is running in my VPC. But we get a username and a password back. And that is a real username and password that I could use to communicate with this database. That particular username and password combination corresponds to the ability to select or read only. If I tried to delete or insert or update, I would get permission denied from Postgres, not from Vault. But what we did is we codified or automated a process that was normally done by a DBA or copying and pasting from Stack Overflow. So now, every time we need a Vault Postgres user, we just ask Vault for it. And that user is valid for 2 minutes, and after 2 minutes, it goes away. So what happens after 2 minutes? Well, Vault's going to go and revoke that credential. So how do you keep that credential around? Like, what is it? Like, this seems bad. Vault shouldn't be just deleting stuff. It should be some human going in and deleting stuff. Well, we found that that doesn't work. When is the last time any one of you actually deleted a production credential? Right? They tend to linger around. Even if you rotate them, we think, oh, we've rotated, we're more secure, but people forget to revoke the old one. So you're not any more secure. So we actually rely on a machine to do this. And we do this through the lease revocation and automation process. I lost my slides. What is this? DevTernity, right? Open images renewal. All right. So this is the process for interacting with a credential in Vault. When you have a process, you ask Vault, hey, do I have a secret? Like in memory, do I have a secret? And if the answer to that is no, you just ask Vault for a new one. You say, hey, can I get a credential? If you do have a secret, you have to renew the lease associated with that secret. That's going to prevent Vault from revoking it. So it's basically like making like a ping or a TTL request to the Vault server, and all you do is say, hey, I'm still using this. It's a very quick call and response to Vault. Hey, I'm still using this. Hey, I'm still using this. And you can do that any number of times up until the lease duration. If you haven't done it before then, you're going to expire the credential because you're going to hit that lease. All right, back to slide land. So this means that an application that wants to integrate with Vault has to implement that flowchart. And that flowchart isn't exactly on the easy side. There's a number of edge cases you have to take into account. So what we've done at HashiCorp is we built a number of tools that act as sidecar applications that present to your application or your web app or your database, whatever, information in a format it's already familiar with, a text file or an environment variable. But that sidecar application is actually writing out that text file or writing out that environment variable for us, managing that renewal lifecycle with console automatically. And this is important, and one of those tools is called console template, which I can show you very quickly. Yeah. So console template goes out and communicates with Vault. It's a terribly named tool, but it generates credentials from Vault, and it can write them to a template. So hopefully, if I type this out right, I should be able to say to console template, hey, the Vault token is root, and I'm going to ask you to run console template with this template in dry mode. Ignore that. We're going to move on. I'll fix that later. The way console template works and the way other applications work is actually by communicating Vault via the API. So before we ran things like Vault read and Vault write, those are actually just HTTP get and HTTP put operations. So the same things I run via the CLI, I can run via a tool like curl. And the way I do that is I type curl, and then the Vault CLI does maintain a little bit of state for us. It stores that token in memory and caches it so we don't have to type it out every time. But because HTTP is stateless, we have to pass that token every time. And that is via a header. So we pass in a header, and that header is xVault token, and the value for that is root. If you remember, that's the token I authenticated with at the beginning. Then we just get back, we just hit Vault at the path that we would have read from. So my Vault server, which I haven't told you this yet, is actually running at vault.hashicorp.rocks. The API namespace is v1, and then everything after this is what I would have typed into Vault. So PostgreSQL creds read only, and I'm going to pipe this to JQ. You'll notice that we get back a response. That's a formatted JSON response. The username and the password is contained in that body. It's just a standard plain old JSON response. So any modern programming language can interact with this tool, pull that data out, write it to a file, pull it into memory, do whatever it needs to do. And just like before, every time we run that, we get back a different username and password. And the same thing is true if we read from AWS creds developer. Right? We'll get back, in a little bit more time, we'll get back a secret key and an access key as well. So the API is really important because it means that we can build any automation around this tooling. Anything we want to do, we can build automation around it. So what kind of automation can we build? Well, I told you this was an interactive session, so let's get interactive. How many people have a mobile device on them right now? Yeah, so you're going to go to the internet. How many people know how to do that? So go to vault.hashicorp.rocks/app. Work, yes. You'll get this thing. What's that? So this is actually hooked up to my Vault cluster. This is using a public Let's Encrypt. So this is a free SSL certificate from the folks at Let's Encrypt. This is a little front end that I ripped off of our own Vault website that makes an API call to Vault through a tiny little Go binary to generate a Vault token and then generate a curl command that you can use to generate a Postgres credential. So if you actually click Generate Token, you'll get a Vault token. This is a real Vault token that you can use to authenticate against my Vault cluster. Then I give you a little curl command that you can run to actually generate a Postgres user. And I'm going to run this from my local laptop instead of the instance that I've been on, just to show you what that looks like. So I'll run this curl command in a terminal. So I'll run this curl command. Damn it. Every time. It's always the little things. Okay, trying this again. If I generate a new Vault token and run this command now, I'll get back a username and password. And this is my local laptop. So I have a publicly accessible Vault cluster, not a best practice. But I have a publicly accessible Vault cluster for the purposes of this demo so that I can show you what it's like to interact with Vault. So I generated a Vault token. I interacted with Vault with that token. And after 120 seconds, that credential is going to expire. And after, I think, 30 minutes, that token itself is going to expire. So this is the general interaction with the Vault, and because it's an API, the possibilities are truly endless. It's a JSON API, so whether you're a .NET, a Java, or a Scala developer, you can still work with JSON. I know it's not XML, it's not XML, but it is an API, and you can interact with it and do whatever you want. So that's all I have. You can feel free to play around with that vault.hashicorp.rocks/app. You can keep clicking Get Vault Token and notice that you'll get a new one every time. And you can try to DDoS it. No one's been able to yet, so good luck with that. That's all I have. Are there any questions?
So we have 4 questions in Slido.
Okay.
Yeah, how to manage secrets for different environments, like staging, production, whatnot?
Okay, so
with the same backend provider.
Yeah, so that's a good question. Generally, you run one Vault cluster per environment. So you would run a Vault cluster for each, for production, you would run a separate Vault cluster. For staging, you would run a separate Vault cluster for QA. The result is that you have to configure that backend, 3 times or 4 times. Each environment has to configure that backend. I just wrote a blog post last week that actually talks about how you can use, I'm trying to type with one hand, that talks about how you can use basically bash and some simple file structure to mirror those policies. So if you just take a look at this post on the HashiCorp blog, it actually talks about how you can codify that configuration. So those commands I ran, vault read, vault write, vault config, you can put those in a text file, and I actually have an example repo here that you can pull from so that you can just run that script against each environment and you get the same configuration.
Okay, next question. How to make sure that when you generate the master key, like the shares of the master key, that they're not copied by a single person?
Yeah, so that's a really good question. If I'm the person initializing the Vault, when I run Vault init, all of those key shares are going to be printed in plain text, so that kind of defeats the purpose of no one person having complete access in the system. Vault 0.2 and plus, which we're on 0.6 now, supports PGP encrypted unsealed keys. So what you can do is when you initialize the Vault, you can pass in a list of PGP keys from Keybase or stored on the system, and like MIT, and it will PGP encrypt with a public key each key share in the order that you specify. So you give that to whichever person the PGP key corresponds to. They decrypt that using their PGP private key, because that's how public key, private key encryption works. And then you never see any of the unsealed keys in the plain text, and you can't decrypt them because they're encrypted with everybody else's public key unless you happen to have all of their public keys, in which case, or all of their private keys, in which case, why would you have that?
Okay, next question. So if you have like a long-running web app with some connection pool to a database, how do you manage renewal? How do you manage getting the secret?
So there's a couple different answers there. It depends on how you run the app. If you're using a sidecar application like console template or env console, that process will manage the renewal and the lifecycle, and it'll just write out a template. So your application just reads from a template at boot, like if it's a Rails app or a Django app, it just reads that YAML or JSON file in, and then it connects to that database. Whenever that file changes, because the secret was modified or changed or revoked, the console template sidecar will write that template out again, and then it will signal the application with something that's configurable. It'll send some syscall to it, it'll restart it, it'll reload it, anything you want. You can run any script. And in that case, your application needs to drain the connections that it has gracefully, then it has to reload its configuration from that file on disk. Now, if you're like a distributed systems thinking person, and you're like, oh, thundering hard problems and all of these things, there's a bunch of stuff built in that prevents that from happening concurrently across all of your nodes so that you don't have downtime. There's a bunch of stuff built in. Like, we've solved this problem. I just don't want to get into like the super nitty-gritty details because it's kind of confusing.
Okay. Next question, what are the supported backends and how can you add more?
That's a really good question. So Vault's website is vaultproject.io. I just pulled it up here on the screen. And if you go to the docs, on the left-hand side, on the bottom there, you'll see 3 backends. There's Audit, Auth, and Secret. Secret backends are probably what you're talking about, and these are the built-in ones. So we have AWS Cassandra Console, Cubbyhole, Generic, MongoDB, MS SQL, MySQL, PKI, PostgreSQL, RabbitMQ, SSH, Transit, and Custom. I can say all 50 US states in alphabetical order in less than 15 seconds. So we already saw AWS Postgres. Before, like MySQL, MongoDB, MSQL are all going to behave similarly to Postgres. Console will generate console keys. Generic is the generic secret backend. Things like SSH and Transit are interesting, and PKI. So with PKI, Vault can actually act as a certificate authority. It can generate public TLS certificates and private TLS certificates and generate them and manage the CRLs for you. SSH, Vault can actually wrap OpenSSH. And instead of logging into SSH with a public key or a username and password, you log in with like GitHub or LDAP or any of the authentication backends. And then Vault controls your lifetime of that session. It does auditing and logging of the whole process. Transit is like encryption as a service. So it behaves a lot like Amazon's KMS. You give it data, it encrypts it and gives it back to you. It doesn't store it. It's your responsibility to store it. So that's good for encrypting like large blobs of data, or in a web app, that's a very common way to encrypt data. On the authentication side of things, so how do you actually log into Vault? App ID and app role are mostly for machine authentication. EC2 allows you to authenticate against the EC2 metadata API. GitHub and LDAP are obviously familiar with. You can actually log in with a certificate, or you can log in directly with a token or a username and password. And I think the second part of the question is, how easy is it to write your own? Vault at this time does not support a plugin architecture. It's something we're working on, but we have to solve cryptographically secure plugins first, because if Vault supported a plugin architecture, that would mean the plugin would have access to the core, which creates a security vulnerability. So we have to find a way to make sure that those plugins are cryptographically secure before we bring them into core. However, Vault is written in Go and all of the dependencies are vendored. So if you do have your own backend, you have some custom implementation that doesn't make sense to contribute back to open source, you can always compile Vault from source with your own custom backend. And it's very easy to do. We have a number of customers who have some internal services that they wrote a backend for. You just have to implement create, read, update, delete, and it's pretty easy.
Okay, yeah, next question. Is there any integration with Kubernetes? Or will be?
Yes.
For any reason.
Who asked the K8S question? So you know Kelsey Hightower? Do you know Kelsey Hightower? No, he did. Okay. So you should definitely follow Kelsey Hightower. He's the senior developer advocate for Kubernetes at Google. But we've been working together, we as in like HashiCorp, with him. And he just did a proof of concept on interacting with Vault and Kubernetes. So let me find it in like his billion repos. Yeah, so he wrote this Vault controller for Kubernetes, and it's going to be in core soon.
Is that for running Vault in Kubernetes or managing Kubernetes?
Managing Kubernetes secrets using Vault. As far as running Vault under Kubernetes, I think there's a number of community contributed, I forget what they call them, YAML files of things.
Okay, I think we're actually running out of time, but we still have like 6 questions in Slido. Do you want me to ask them, or do you like guys to just come to Seth and ask them afterwards? Ask? Okay. So can you delete only some of the keys from roles, like AWS roles developer, like the one you had?
Yeah, so everything's path-based. So you have to explicitly grant someone access to delete, and you have to grant them delete on that path. So if you grant them delete on AWS Creds developer, but not AWS Creds DevTernity, they won't be able to delete on that path.
Yeah, but can if you created several developers with that
Oh,
role?
can you just revoke a single one?
Yeah.
Yes. You notice whenever I ran one of these commands, yeah, so like whenever I generate this credential, it comes with a lease ID. You can revoke that lease ID.
Mm-hmm. Can you show an example of audit log for Vault?
Of what?
Audit log, like,
Oh, the audit log?
yeah.
Sure. If I can remember how to do this. So the audit backend isn't enabled by default. So I will just, okay. So I enabled the audit backend now. So if I hopefully no, it's called audit.log. Oh, this file exists on that Vault server, not locally. Look, you all get to see Terraform. You didn't think you'd see a Terraform demo. Okay, so this is the actual Vault server. So now if I there it is. Yeah, so the audit log is here. It's just, damn you. Okay, there's no JQ on here. Y'all are. It looks like this. It's just JSON. It includes the request and the response. And the first entry in the audit log is actually the request to enable the audit log. It's a little meta. But it includes, for the secret data, for things that are sensitive, you'll notice that their values are HMAC'd. So it's an HMAC SHA-256. And then there's an endpoint in Vault that will let you generate an HMAC. So you can't reverse engineer this. So if someone gets a hold of the audit log, they can't get the secrets out. But if you know the secret or you know the token and you're grepping the audit log or searching the audit log for it, you can ask Vault to generate the HMAC, and then you can find the entries in the log.
Okay, I think we have to end here because we're running out of time. Please, thank you. And while you leave, please don't forget to vote. Thank you.